I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Good evening, Wondernauts. Thank you for coming this evening. Welcome to Ask a Science Envoy, Poison Frogs and Quantum Chemistry, presented by Wonderfest and by the Berkeley Public Library. I'll tell you a little bit about Wonderfest in a moment, but first, let me introduce Sierra Campagna, librarian at the Berkeley Public Library, to tell you about their involvement and other events happening at the library.
Hello, thank you, Tucker. It's been such a fun partnership working with Wonderfest in Berkeley Public Library. There's always such interesting topics, and it's really especially exciting to have the Science Envoys presenting. So thank you very much for working with us. I just want to tell you really quickly, if you don't have a library card for Berkeley Public Library, you don't actually have to live in Berkeley. You can get an online card and have access to all sorts of things. You don't have to come into the building at all. This is a little secret I know that not everybody knows, is that you can get library cards at many library systems and have access to ebooks, articles, databases, streaming movies, music, all sorts of resources. So I just wanted to encourage everyone, if you don't have a Berkeley Public Library card, to go ahead and sign up for one. It's very easy and only takes a minute. That's all I've got tonight.
Excellent. Thank you, Sierra.
Sure.
I want to welcome you recent arrivers, to Ask a Science Envoy, Poison Frogs and Quantum Chemistry. You've just met Sierra Campagna from the Berkeley Public Library, and I'm Tucker Hyatt, founding director of Wonderfest, the Bay Area beacon of science. I haven't done this before during these Ask a Science Envoy presentations, but I want to reveal Wonderfest's four-point nonprofit mission statement. Wonderfest inspires curiosity, promotes careful reasoning, challenges unexamined beliefs, and encourages lifelong learning. If you'd care to learn how Wonderfest puts some, or let's say brings those rather lofty ideals down to earth, please check us out at wonderfest.org. Here comes our first speaker. Stanford biologist Billie Goolsby will present Family Feud, Familial Decision-Making in Poison Frogs. Billie earned her undergraduate degree in biochemistry and molecular biology with a minor in sociology at Boston University. She is now a fourth-year PhD student in Stanford's Laboratory of Organismal Biology, working with Professor Lauren O'Connell. Please welcome biologist, frog lover, I suspect, and Wonderfest Science Envoy, Billie Goolsby.
Thank you so much for that introduction, Tucker. So my name is Billie Goolsby, and I am an organismal biologist. And today I'm going to be sharing some of my PhD work in poison frogs, family decision-making. So like I just told you, I am an organismal biologist, which means that I am interested in using animals to better understand what makes us human. And so people use organisms across the vertebrate and invertebrate lineages to better understand a diverse range of behaviors. And so this includes agonistic behaviors, such as affiliation, breeding, parental care, but we can also look at antagonist behaviors, such as fighting, territory defense. And so what I'm specifically interested in is the emergence of biparental care, which is when moms and dads have to work together as a team to care for their offspring. And so this has evolved both in invertebrates and vertebrates. So my biggest question for my PhD is, what makes a good parental team? So you might be asking yourself why I would study this in poison frogs. But poison frogs actually have a diverse repertoire of behaviors that they do. So for example, we have egg care. So fathers will guard their tadpoles from fertilization all the way until hatching. And so you can see this father guarding his bounty of eggs here. They also do tadpole transport, which is when mothers or fathers, primarily fathers, will put their tadpoles on their backs, piggyback style, and navigate throughout the rainforest. Finally, my favorite, which is the one I'll be talking about today, is egg provisioning. And so this emerges in low resource environments and has emerged across poison frogs multiple times in response to low resource environments, where poison frogs provision unfertilized egg meals to their tadpoles. And so you can think about this as somewhat of a form of nursing, because they're providing a physiological resource to their offspring. So just to kind of illustrate what this looks like in sequence, we have this father who's guarding his eggs that have been laid on leaf litter in the rainforest. So he's going to take this tadpole after it's hatched from its egg onto his back. And then he has the task that, this is just a video I wanted to show the audience. This is actually what it looks like. So the tadpole's like whipping around and like hanging out on the dad's back. This parent has to navigate throughout the rainforest to deposit these tadpoles into individual pools of water. And so this requires a high level of navigation. And so what happens with egg provisioning species is that poison frog parents will visit their nurseries where the tadpoles are deposited every few days until they metamorphose. And then tadpoles will beg for food by vibrating. And so based on this vibrating sequence, parents, specifically moms, will feed tadpoles unfertilized egg meals. So I just described begging to you, but I want to expand on what that actually looks like. So in this video, you see tadpoles begging for food using these rapid body vibrations. So I want to just highlight it here, where you see this tadpole intensely shaking its body against the mom. And so if that begging is successful, mothers will deposit unfertilized egg meals. So this is a tadpole that's been very lucky and has successfully gotten a meal from their parent. And so they just eat it bite by bite. So like I was telling you, what I'm specifically interested in is how poison frogs model monogamy and biparental care. So my question is, what makes a good parental team? So I specifically study a species called Renitomea imitator, or the mimetic poison frog, which is biparental and monogamous, where they work together to care for their offspring. So I want to show you a video of how this actually happens in the wild. So before I start this video, I want to tell you that the male is the one that calls and the female is the one that nurses. And so you can actually see them working together to convey information about a begging tadpole that is inside of this bromeliad, this plant, inside of the water. You can see the tadpole's body right here. And so what we just saw was the father calling the female to the nursery where the tadpole is. And so to show you what the begging looks like in the tadpole, it's this intense vibration. And then if it's successful against the mom, the tadpole gets eggs. So we see the emergence of two unique traits based on who the parent is. So fathers have the unique trait of being able to call. Mothers have the unique trait of being able to nurse. And so what this means is that teamwork is required for males to call females to where the tadpoles are, to tell them that the tadpoles are hungry. And so previous work has shown that if the father is removed from the situation and teamwork is broken, offspring mortality for tadpoles increases to about 70 to 80%. And this is an underscore of how important teamwork is in this species. So all I've shown you so far with this question is that we know teamwork is important to some degree. If we remove males, the team falls apart and tadpoles die. But we actually need to develop a metric for what good parenting actually is. So I want to tell you about an obstacle that I faced during my PhD, because small successes are successes nonetheless. So poison frogs are ectotherms, which means that they don't produce body heat, unlike humans, which are endotherms, which do produce heat. And so what that means is that a lot of recording technology actually relies on heat, to be triggered and to record behavior. And so what this means for my research is that I had to develop an entirely new tool in order to record behavior in my frogs. And so we actually devised something that was very affordable, which was just reusing home security cameras and using them as a new behavior tool. And so we were able to use them because they can withstand high humidity and high heat environments. And so we're able to actually suspend these cameras above tadpole nurseries and record this behavior repeatedly and consistently to do behavior recording and quantification. And so, for example, what you see here is the male, the female coordinating care, and it has been successful. And we see that an egg has been fed. And so something that I want to share that's even more exciting is that a postdoc in the lab was able to bring this to the field. And so I actually want to show you how we can parallel field work to work inside of the laboratory. And we are able to identify entirely new behaviors that weren't described for this species. So I'm going to play this video that was recorded from French Guiana. And so this is a recording that's suspended directly over a bromeliad nursery. And so what you're seeing inside is an intruder inside of this nursery home. This is a poison frog that is 5 to 10 times bigger than the male, and that's not going to stop him one bit. He is going to make sure that this much bigger poison frog gets out of his home. And so I'm going to just fast forward the video a little bit, because what you're going to see here is that poison frogs fight like gummy bears. They don't, have any sharp features. They just wrestle. But you see that this father is very committed to getting this much larger intruder out of his home. And so this just is underscoring how much of dedicated fathers these poison frogs are. So from my laboratory research, and I did this in collaboration with an undergraduate researcher that I had hired, we recorded different families in these habitats in our labs. And we recorded over a span of 30 days, what were the normalized amount of visits each parent was visiting their tadpole. And so what we found is that fathers are the ones visiting the most. And we see the father's visits in dark green, the females by herself visiting in light green, and then together as a family unit in purple. This is the rarest kind of visit, this coordinated effort together. But what is really exciting is that we can compare across these days that we've recorded, from just your average day to when egg feeding is actually happening, because it only happens once a week. We can see what happens on those days, and then we can see directly the day after egg feeding to see what happens in terms of parental care effort. So your average day, it looks like what I just showed you. So fathers visit the most, mothers are somewhere in between, and then family visits are the rarest. On egg feeding days, we see that flip. So family visits are the highest, and this makes sense because moms and dads are working together to try to coordinate care. But something really striking happens the day after egg feeding. We see that family visits absolutely drop. And so this is also when fathers visit the least. And so we find this really striking because what it tells us is that fathers must have some way of knowing when mothers have actually fed their young. And so this decrease means that he's no longer trying to coordinate care because he knows that the tadpoles have been fed. And so this actually tells us that fathers have some metric, which we still don't know truthfully, of evaluating maternal effort. And so this is quite a sophisticated behavior to do. So now we've developed this metric of good parenting, which is that we have high visitations by fathers, we have an accurate evaluation of feeding, we have a higher level of feeding. So a very invested father will coordinate care for their tadpoles to be fed every 5 days. A horrible parental set will never feed for 30 days. And so what I wanted to know is that we're seeing this change in parental care effort, and it's based on family. Why does that matter? So it could be that tadpoles are totally fine, independent of what the parent is doing, or they might entirely rely on how well their parents work together. So what I did was I looked at investment patterns of moms and dads and families and divided them based on whether they were high care or low care. So the green that I'm going to show you is family visits that accumulate over time. A dotted green line is when they're low care. Similarly, dads are blue. Solid line is a high care dad, and a dotted line is a low care dad. And so what we see is that over the 30-day span, high care families and high care dads have a much higher slope or more visits that accumulate over time compared to low care families, which are much smaller, which means that over the 30 days, tadpoles are only going to be visited maybe 10 times. And so what this tells us is that high care dads are really dictating how much care the family provides. And so I'm going to juxtapose that to what females are doing. So we can compare high care dads and low care dads, just like what was in the last figure, to high care moms and low care moms. And so we are interested in this to understand if there's a compensation that happens between partners if one partner isn't doing their job. And what we see is something that's not the case, which is actually high care moms and low care mom families are actually individually contributing equal amounts. And so this is also informative for us because it tells us that low care moms will not compensate for failing fathers. So if the dad is not present, the mom is not going to change her behavior to provide care for the offspring, which could be a reason why they're still low care. Okay, so we see this relationship between investment, but we actually want to see the impact on tadpoles because this is the next generation of frogs that come from this team. And so we can look at the synchronized level, so this is synchronized number of visits, and compare how many eggs are fed. And so we see that there's a positive correlation between the more synchronized a pair is, the more often they're going to feed their tadpoles. And so we see a modest correlation with tadpole weight as a consequence. And so tadpole weight is a great indicator for survivorship because it means a tadpole has way more food resources and nutrients to metamorphose into froglets. Okay, so before I share this next bit of information, I want you to recall how there was a much bigger poison frog that was invading that nursery, and the dad was fighting to get that bigger frog out of there. And the reason that's the case is that much bigger frogs cannibalize smaller tadpoles from different species. And so the reason that this is striking to us is that tadpoles, like I just showed you, do this intense vibrating behavior, right? And so this is a very visually and tactile dazzling display. And so tadpoles have to be very careful about who they do that to, because if they do it to the wrong frog, they're going to get killed. And so what we see then is we can compare how this begging behavior that tadpoles do change when they're exposed to strangers or their parents. And so we wanted to see how tadpoles that were raised by good parents have a preference or not versus tadpoles that were raised by bad parents or not. So in other words, would we see if they have a preference for their moms or dads based on how they're raised? And so I want to show you this parental preference score where the more purple a box is, the more a tadpole has a preference for their biological parents versus a stranger. The more orange a box is, the stronger they have a preference towards strangers. And so this is more risky behavior on a tadpole. And so what we see is that tadpoles that are raised by good parents have a preference towards their moms. On the other hand, when tadpoles are raised by bad parents, they have a preference for strangers. And so we are seeing the multi-generational effects of teamwork and how tadpoles interact with the world and make behavioral decisions. So we're beginning to see the consequences of parental teamwork in this poison frog, which is that offspring behavior and success is shaped by how moms and dads work together as a team. But this is a reciprocal relationship because parents are also getting information from their offspring. And so a question that I have is, how do parents recognize their offspring to make these decisions about whether to provide care or not? So this is some excellent work that was done by another one of my undergraduate researchers, where she took these poison frog families. And so a positive control is just measuring the effort that they give their offspring just over the span of 30 days. A cross foster is when she takes those offspring between two families and switches them. A cross morph is when you do the same thing of switching, but this is just when there's the same species, but they look slightly different. That's all you need to know about a cross morph, is that they have a slightly different coloration pattern, but it's the same species. She also did spatial moves, which is when you take a tadpole and move it within the same tank to a slightly different area. So that means that the same biological offspring are there, but they're in a slightly different place. And so she found something really interesting, which is that there's no difference in how parents care for their offspring if they're cross-fostered or if they're cross-morph. But parents will absolutely abandon their young if they're spatially moved. And so what this tells us is that space is a really important way for parents to recognize their young, rather than using direct kin recognition like smell or something else where they can actually identify who's their young. They're using space. So we can actually exploit that. So because poison frogs recognize offspring based on location and not direct kin recognition, we can not only replace the tadpole with just another cross-foster, but we can add a robotic infiltrator. And so this is current work that I'm doing with Tony Chin, who's a mechanical engineering student at Stanford. And so we can add a robotic tadpole inside that directly mimics begging. And so this is the robotic tadpole that we're using to mimic that behavior. And so I just want to show you as a proof of concept, this is work that's actively happening right now. But does it trick the frogs? He's calling, he thinks it's real, and he's trying to coordinate care of this robotic tadpole. And so this is kind of the next step in what I'm doing in my PhD. So I see that they're recognizing tadpoles based on location and not kin recognition. And because I'm able to actually control the signals that tadpoles give with RoboTad, I can change the begging. I can begin to ask some new questions. So my next question here was, how are parents interpreting this begging signal when making familial decisions? So to do this, it requires some neuro. And so I'm interested in what's changing in the brain in response to this begging stimulus. So I take poison frogs and I expose them to a begging tadpole. The control is being exposed to a tadpole that's not begging. And then I do some studies of what's going on in the brain. So you don't need to know the names of these specific things, but what's in pink is what's higher in brains of poison frogs exposed to begging. And so a lot of what is in pink are actually neurons in the brain related to sensations of pleasure. And so what this is telling us is that offspring touch, so the begging sensation, could feel good the same way that babies cuddling their moms feels good to humans. And so the next test that I want to do is using RoboTad as a way to manipulate opioid signaling pathways. So this is the specific pathway that's being used. And so we can interact frogs with opioid signals and pharmacology, so giving them morphine or not giving them morphine, and then exposing them to tadpole begging via RoboTad to better understand if poison frogs pursue begging tadpoles and snuggle with them because it feels good. So this is the current state of my work. And so what this tells us on whether parents are actually relying on begging signals, it seems like yes, and it's likely a pleasurable sensation, but we have way more testing to do in answering this question. So with that, I want to thank my lab, which is amazing and always so supportive of my work. I also wanted to thank my committee, Dr. Lauren O'Connell, Dr. Alejandro Velez-Melendez, Li Chun Luo, and Robert Sapolsky, as well as my funding resources. And I also want to thank Tucker for letting me join the Science Envoy team and share my science. So thank you, everyone, for attending.
You are very welcome, Billy. I'm so glad you became a Science Envoy. Thank you for that presentation. We have a question already from a multi-talented wondernaut who comes up with great questions and who I believe at this moment, as he says in his listing of participants, in the continent that shares your source of poison frogs. At least some of them come from British Guiana. Our wondernaut, Stuart Usum, is in Guayaquil, Ecuador. Stuart, I'm so impressed you're coming in from so far. Welcome. Please ask your question.
Yes, glad that the timing worked out perfectly. So yes, really thrilled by your research, Billy. So my question, as in the chat, is so these bi-parent interactions, are they always between a mated pair, or would a male possibly attract other females too? And let me just, I'll finish. I got multiple questions. You can answer them if I'm allowed all this time. Thank you. How do the father frogs remember all the locations? How many locations are there of the tadpole nurseries? Are they always only one tadpole per bromeliad location? And did you notice if there's any other signaling between the tadpoles and the parents, such as hormones, smells, or sounds? Thank you very much.
Yeah, thank you for all these questions. I love talking science, so this is, it's so fun for me. So your first one was about biparental interactions, and so is this specific to the mated pair of frogs? So there's a couple things I want to say. The first one is that these poison frogs are incredibly territorial. So they push out any of the non-mated frogs that are actively courting from their territory. So they like wrestle, they do the gummy bear wrestling, even within their same species. Now, that being said, there have been studies in a closely related species to this showing some form of parasitism, where fathers will try to coordinate care with females that aren't the mated partner so that he can get eggs that are not hers fed to his tadpoles. And so basically he's stealing a resource from a female that's not the one he's mated with. And so that has been seen once before in a closely related species. But for this specific model, they are genetically monogamous. So people have basically tried to see if they cheat each other. And so the evidence points to no, they're actually very faithful. So it's probably a balance of, opportunity and also something else that we can't understand quite yet. So it's a little bit of yes and no there. Your second question was, how do father frogs remember all of the locations? This is actually a great question, and we don't know. It's part of what our lab is studying. It seems like it involves the amphibian version of the hippocampus. So it's called the medial pallium. And so there's current work just trying to understand, because like you said, it's an incredibly complex task. If we were to think about it in the context of humans, it would be navigating a university campus to find 5 different parking spaces where you've left your babies. And they're all over campus. And that is like a massively difficult task. And so we still don't know why or how that happens. But the most we're looking at for this species is potentially 6. But the average is maybe 3 or less. And so for this specific study, we controlled how many offspring they were able to care for at a time. So we didn't have those variables. But yeah, they're able to do that, and we have no idea how. Are they always using only one tadpole per bromeliad location? Yes. And the reason is that the tadpoles cannibalize each other. So if you look up these tadpoles, they actually have teeth like a shark. So they have little rows of teeth, and so they will use it to take chunks out of each other. And so sometimes we'll see things where like a poison frog tadpole will like be deposited as like a meal for another tadpole, which is very grim. But in most cases, what we're actually seeing is a father trying to separate them so that they all have a chance at success. And so then your final question was, are there any other signals from tadpoles to parents, such as smells or sounds? So poison frogs love using smell. It's one of their primary drivers. They also have great vision. And so we're able to kind of mask that with RoboTab because we can just take tadpole conditioned water and just dunk it in there. And so then the male's like, great, that's my baby. The mom's a little more unconvinced, but that's what current research is on now. So in terms of sounds, I don't think so, because they use slightly different modalities, fish versus land walking animals. They have different ears. So I don't think that's the case, but definitely olfaction for sure. It's actually one of the ways that poison frogs make decisions about where to best place their babies, because they want to have a nursery that's full of leaf litter and other detritus that is enriching and nutritious for the tadpole.
Stuart, great questions. I'm going to ask one so much more basic than what you put forward. Thank you for those questions. Billy, I'm afraid I'd like to understand in what sense a poison frog of the type you study is poison. Clearly, they're eating each other on occasion, and the image of a robo-tadpole or a living one that's a gummy bear with teeth is terrifying. But in what sense are these frogs poisonous? To whom are they poisonous?
Yeah, oh, great question. So the poison frogs that we work with in captivity are not toxic. And the reason that they're not toxic is because poison frogs don't organically make their toxins. They actually sequester them from their arthropod diet. So in other words, they're eating ants and mites and other critters in the field. And so that's actually where they're getting their toxins from. And so in the lab, we give them Drosophila, so that's just your average fruit fly. And so when they're fed fruit flies, they don't become toxic at any point. And so the poison frogs are toxic and aposematic. So aposematic means that they have this bright, dazzling coloration, and it's actually a signal, right, that I am so colorful because I can be. And so it's almost an active threat, right, because they're often poisonous too. And so they are toxic to things that try to eat them. So that includes humans, includes birds, any other type of critter, right, that would think a frog would be a tasty treat. And so they're actually not toxic to each other in this circumstance. So when they're fighting each other, they're not using their toxins. They're actually physically wrestling and trying to drown each other. So poison frogs are not aquatic. They are terrestrial. So they love humidity and moist environments, but they'll drown if they are shoved into water long enough. And so that's what these males are actually trying to do to each other and prevent food intake in order to fight one another. They don't use their toxins with each other. It's mostly to keep predators away.
Wow. Forgive me for anthropomorphizing these poor creatures, but while we give them points for being monogamous and good parents, man, they're not quite fully civilized by our standards.
Oh, they're merciless.
Billy, thank you very much.
Yeah.
We're going to move on to our second presentation. Our second speaker is UC Berkeley physicist Ashwin Singh. He will be presenting Exploring Quantum Chemistry with Earth's Strongest Laser. Before coming to Cal, go Bears, Ashwin earned a Bachelor of Science degree in mathematics and physics at the University of Sydney in Australia. He also worked at the Sydney Observatory, showing people his love for the southern stars. He says they're clearly in the best hemisphere. Now Ashwin is completing his PhD with Cal physicist Professor Holger Mueller. Please welcome physicist and Southern Star lover, Wonderfest Science Envoy, Ashwin Singh.
Thanks so much for that introduction. So this talk, the title of this talk has two main parts to it. It has exploring quantum chemistry, and it has Earth's strongest laser. And don't worry, we'll get to the world's strongest laser in just a little bit, but I want to start with the exploring quantum chemistry side of this talk, because it sort of represents a hole in the bottom of our understanding of chemistry and chemical reactions. And to understand what I mean, let me tell you a little story. This is a story about a hypothetical interaction between a chemistry professor, this man on the right, and his son, the little boy on the left. And so this chemistry professor comes home from work one day. He says, "Son, look, I just did this beautiful reaction. And it's very complicated." And he goes on for a very long time about all of the details of the reaction. And his son says, "How does that work?" And he realizes that his son is not a lab mate of his, so he should simplify it a little bit. And he says, "Oh, it's just a special kind of reaction, which is of this class." And he talked a little bit about something called arylation that his son doesn't really understand. And his son says, "How does that work?" Now, this chemistry professor decides, okay, maybe I should simplify a little bit more and talk about how chemical reactions work. And he says something like this: "I start with some reactants. They are things that are going into a chemical reaction, and they have some amount of energy. Maybe I give them some heat or a little kick or something like that. I give them some extra energy so that they can crash into each other, break some bonds, and form new ones. And then the reactants can become products, and that's how a chemical reaction happens." Now his son asks again, "How does that work?" Now the professor is getting a little bit stressed out, not because he doesn't like answering all these questions, but because we're reaching the bottom of this pyramid. And he says, "Well, how do reactions happen?" Well, when you take two molecules and you collide them, they crash into each other in just the right way, with just the right orientation and just enough energy, they can break some bonds, form new bonds, and undergo a chemical reaction. And now as silence hangs over the room, the professor crosses his fingers behind his back, hoping that his son is not going to ask one more question. But he does, and he says, "How does that work?" And so the professor says, "Go ask your mother." Now, fortunately, this professor is married to a physicist. So here he comes with his son, and he goes and meets his wife, and he says, "Hey, can you help me explain all of the difficulties of how reactions actually happen? Tell me what you know about quantum mechanics." And she says, "Quantum mechanics, that's easy. All I have to do is solve this equation. It's called the Schrodinger equation." And she goes on a very long tangent about that. And he says, "Okay, but can we talk about something that's actually useful? Tell me about atoms and molecules." Now she's a physicist, and so she says, "Atoms, you're talking about hydrogen. You see, physicists think that there's only one atom that exists, and it's hydrogen. They only like to think about one nucleus, one electron, and everything else is a little bit too complicated." So she says, "Look, this is a hydrogen atom. It has a nucleus, it has one electron, and I can write down all of this maths and tell you exactly where the electron is likely to be." And he says, "You know, there are things that aren't just hydrogen atoms, right?" And she says, "I guess so. I guess helium is something that exists." And so she tries to put one more electron on her atom, and she says, "Well, this makes things a lot harder." So she goes to her computer, she does lots of calculations, lots of simulations, and after a few hours, she comes back and she says, "Okay, I was able to roughly get where electrons sit in a helium atom, and it looks something like this, but it was really hard." And he says, "Are you seriously telling me that the most complicated thing you know how to do is a helium atom? You can tell me where two electrons are in an atom?" And she says, "Let me do some research." And so she goes and looks in the literature, and she spends hours looking for the right papers and what the smartest people in the world have done with the best supercomputers. And she says, "So I think this is how oxygen molecules work." And so the chemistry professor says, "So how do chemical reactions happen?" She says, "I don't know." And so we're in an impasse here. And what's so interesting about this is that we have a problem, which is how do chemical reactions really happen using quantum mechanics and everything, all of the complexity of it? How do chemical reactions really happen? It's a problem that is sort of too easy for chemists to solve because they don't need to solve it to actually do chemistry in the lab. And, the chemistry that they actually do isn't necessarily, it doesn't really care exactly how every reaction happens. But at the same time, how do reactions happen is a problem that's too hard for physicists to solve. It's hard enough for them to solve helium atoms, let alone how chemicals collide and form new chemicals. And that is where chemical reactions in quantum chemistry lie. It's at this realm of things that are too hard to model, but kind of too easy to see in the lab. And another way of framing this conundrum is that the quantum chemistry of chemical reactions is an area where we have too little data from chemistry in the lab to say anything, and really limited models from physicists to say anything. And so it's a very difficult field to study. Let me give you maybe a little bit of context. What is quantum chemistry? What is the realm of quantum chemistry? Let's start by thinking about what regular chemistry looks like. And for a little picture, you could imagine doing a chemical reaction in the lab, like in high school or anything like that. You have a test tube and maybe you fill it with some water and some chemicals. Now, in about 30 milliliters or 1 ounce of water, there's about 1 septillion H2O molecules. So that's 1 with 24 zeros after it. The realm of quantum chemistry isn't concerned with this. It's concerned with what happens when you have single molecules colliding with each other. So you have to get rid of like loads and loads and loads of molecules and just look at single molecules colliding one at a time to see how the quantum mechanics really works between them. Similarly, in kind of regular chemistry, we often do chemical reactions at room temperature, or we heat them up. So often in chemistry class, we turn on a Bunsen burner to start a reaction happening. In the realm of quantum chemistry, we're not interested in heating things up. We're interested in turning the thermostat all the way down to 1 Kelvin. That's 1 degree above absolute zero, or about minus 458 Fahrenheit. We're talking about really, really cold chemical reactions between single molecules. That's the realm of quantum chemistry. But you might ask the question, what is there any system that actually behaves like this? Is there any real system that actually has single molecules colliding at a really cold temperature? And there's no system on Earth which is like this, except maybe in the lab, but there is one in outer space. Outer space is full of chemical reactions just like this, where you have a very low density of molecules in outer space. So molecules are really colliding one at a time. And everything is really cold at about 2.7 Kelvin. So this is the kind of picture that we should have. We're talking about the chemistry that happens in outer space. So you might ask the question, well, does anything actually happen when I'm doing chemistry at a really cold temperature? In my chemistry lab in high school, we would use a Bunsen burner to make reactions happen. Why should anything happen at cold temperatures? And the intuition we have there is that, if a chemical reaction involves molecules colliding with each other, breaking bonds and then forming new ones, it stands to reason that when things are really hot and all the molecules are colliding with each other really fast, then they're more likely to break bonds and form new molecules. So when something is really hot, you expect that chemical reactions are more likely to happen. On the other hand, when something is sort of at a medium temperature, you expect chemical reactions to be pretty slow. And when something is at a very cold temperature, you expect chemical reactions to be extremely slow and basically not happening at all, because it's just really unlikely that these molecules are going to collide with enough energy to change their state, to change their chemical state. And this is something that we believe so strongly that we called it Arrhenius's law. Okay, so it's not just Arrhenius's theorem, it's not just someone's theory. This is Arrhenius's law. We are so confident in this rule, that when things get hotter, reactions happen faster, and when things get cold, reactions happen really slowly. We're so confident in this that we called it a law. And this applies to all the chemical reactions that you've ever done in a chemistry lab or in the kitchen. I'm basically 100% sure that that's true. This applies really generally to any kind of chemical reaction. And in fact, It applies even beyond simple chemical reactions like you might do in the lab or in the kitchen. It applies to really complicated systems. There's sort of a fun trick that you can do, which is if you want to know what temperature it is outside, you can listen to the rate at which crickets chirp. And the reason this works is because fundamentally, what is a cricket? It is made up of lots of different chemicals. It's made up of lots of different chemical reactions. And so the rate at which the crickets chirp is actually dictated by the temperature, by how hot it is outside. When it's hotter, their chemical reactions happen faster, and so they'll chirp faster. And when it's colder, they'll chirp slower. And just because Billy was telling us about frogs, it also applies to frogs. It applies to frog embryogenesis, for example, the rate at which embryos are formed in frogs. And I'll let you think about all of the other places that Arrhenius's law applies. Things happen faster when things are hotter. So that's it. No chemical reactions happen when it's cold, so we don't need to study quantum chemistry, which only happens at cold temperatures. And that's the end. That's the end of the story, and I've wasted my time doing research on this topic. Well, obviously I don't feel that way. So let me tell you something where Arrhenius's law maybe goes wrong. What we're looking at here is a graph of reaction rate on the y-axis. That's how fast does a reaction occur. And on the x-axis, the left side is hot, the right side is cold. You can see the actual temperature values at the top of the graph that correspond to the different points on the x-axis. And we're looking at one particular reaction, which is the hydroxyl radical reacting with methanol. The actual specifics of the reaction aren't really important here. Just let's say we're looking at the reaction rate, and we're seeing that when everything is hot, the reaction rate is fast, that's on the left. And when everything is cold, the reaction rate is slow, that's on the right. And we can draw this like red curve that I just drew with a mouse over all of this data, which is what Arrhenius's law roughly tells you. Reactions should slow down when things get cold. But you can probably already guess where I'm going with this. Look at all this empty space at temperatures like 80 Kelvin, 60 Kelvin, really on the cold side of this x-axis. What happens there? Well, if you actually measure the reaction rate, it goes up. And it doesn't just go up a little bit. The reaction rate at cold temperatures is faster than it is at room temperature. And it turns out that the only way that you can really explain this is you have to use quantum mechanics. This gray curve is actually from the paper where I took this graph. This is the chemists trying to theoretically explain this data that they have using quantum mechanics. And what you can see is, they can explain the reaction rate going up, but it's still really hard to get the actual reaction rates right. And so all of this is to say is this is a really difficult and complicated field, incorporating all of the quantum mechanics of chemistry and trying to understand how reactions happen. With this in mind, I want to take you back to something that I showed you earlier, which is the realm of quantum chemistry is sort of at the intersection of having too little data from regular chemistry and two poor models coming from physics. And one thing that we can do here is we can hope to at least fix this limited data problem. And that's the goal of the project that I'm working on at UC Berkeley, is to try and give us some more data for how cold chemistry happens. So how do I study the reactions of cold molecules? First thing is I have to get them cold. And so what I'm showing you here is a picture of something called a cryocooler. And it's basically a very special refrigerator which can cool things down to a temperature as low as 1.5 Kelvin. And actually the technology that's used here, part of it called a pulse tube cryocooler, is the same thing that they use on the James Webb Space Telescope to keep it cold so they can take all those really beautiful images. Anyway, that's just a cool bit of trivia. This is a really nice refrigerator, can cool things to 1.5 Kelvin. So here's an idea. Let me put a box in that refrigerator. Let me cool the box to 1.5 Kelvin, as cold as I need to get to study cold chemistry. And let me just put the chemicals that I'm interested in, that's these purple and black things that I'm showing here, into that box and just watch them react. It's simple, right? Well, not so fast. If you did this, then all of the molecules would eventually hit a wall and freeze onto it. We're talking about something that's 1.5 degrees above absolute zero. Almost everything freezes at that temperature. And so you can't actually study individual molecules colliding because they're all stuck, they're all frozen. Now, I said that almost everything freezes at 1.5 Kelvin, but not everything does. Actually, a cold gas of helium, a low pressure gas of helium will remain a gas even at this cold temperature. So we can throw out this idea, and what we can do is instead fill a low pressure helium gas into our cold box, and we can put molecules into the bottom of the box. The molecules are going to crash into the cold helium atoms, and so they will also get cold. And what's really nice about this method is the molecules will only go to the walls very slowly because they're buffered around by the helium buffer gas. So they're crashing into the helium gas all the time, and they just can't find their way to the walls. It takes a very long time for them to get there. But eventually, they will hit the walls, and that's a problem. So what we do need is something that can, some kind of force. I need to apply some kind of force that can pull molecules into the center of this box. And that way I can make sure they stay there forever. I can get rid of the helium and study their chemistry. So the way we're going to apply this force is using a technique which is really popular in physics and also in biology and chemistry called optical tweezers. And it won the Nobel Prize in 2018 because it's such a revolutionary technique. And the idea is really simple. I take a laser beam, I shine it into a lens, which focuses the light down to a spot, and molecules or any kind of matter gets attracted into the focus of the laser beam. The fact is that under almost every circumstance, matter is attracted to regions of very intense light. So everything gets attracted to the focus of a laser beam. The problem is the attraction is really weak. So sure, this gives me a force that keeps my molecules from hitting walls and freezing to them so I can study them, but the force is really small. So let's do two things to fix that. Number one, use a very intense laser and shine that very strong laser into this lens and focus it down. And the second thing we use is mirrors. The idea here is you can see that's us in the lab being very careful with these very precious mirrors. We're going to shine the laser light between these two mirrors so it bounces back and forth. And in fact, we designed these mirrors to be 99.99% reflective. So the light bounces back and forth about 10,000 times. And we get 10,000 times the power. And with all of these things combined, what we produce is the world's strongest laser, by which I mean specifically the world's most intense continuous laser. And before I go to the next slide, I want to tell you, I want to put it a little bit in perspective. So I need to tell you two things. The first thing is the image might give you a little bit of a headache, so don't look at it for too long. I'll tell you when it's over, but I do want you to see this because the picture is really cool. And the second thing I want to tell you is, I guess, setting the scene. When our research group developed this world's most intense continuous laser, it was actually to study electron microscopy. And one of the things they did is they put this laser under an electron microscope. Now, I want you to think, in regular microscopy, what we normally do is we study how light bounces off matter, bounces off the electrons going around atoms, and we can look at the reflection of light and we can tell what something is made of. What we're going to do here is the opposite. We are going to put a very strong laser beam inside an electron microscope, and we are going to use electrons to take a photo of a laser. It's the exact opposite of what we normally do. I want you to picture, what do you think a photo of a light wave might look like? And now I'm going to show you what it actually does. It looks like this. So first thing to say is, I guess you knew that light was a wave, maybe from someone telling it to you, like a teacher, or maybe you read it in a book. But the the reason we know light is a wave is not just because of that. It's because you can see this. You know, with an electron microscope, you can look at the bright and the dark spots. I'm zooming in here, and you can see the bright spots are the crests of the wave and the dark spots are the troughs. And you can see, look, light is a wave. I can see it under an electron microscope. It's beautiful. And this is really all just to show how intense this laser is, that you can actually see it using electron microscopy. This is the first time this has ever been done. And I just think it's a really cool image. I want to get back to what we're actually doing. So you can look back at your screens if that image was giving you a headache, because it's all gone now. The current stage of my research at UC Berkeley is to build this hypothetical experiment that I've just described with the world's strongest laser, picking up very cold molecules and holding them in place, and studying how they collide with each other and how they react. And putting it all together comes in a few stages. So on the left, I'm showing two of my other teammates. That's Lothar on the right and Ziguang, an undergrad. So Lothar is a postdoc on the project. Ziguang is an undergrad, or was an undergrad on the project, putting our very cold refrigerator into a chamber for us to test. In the middle, I'm showing how we construct optics that direct lasers. And this is really fun. It's a little bit like playing with Lego. So you buy some parts, which are a bit like Lego blocks. You put them on this board with all of these slots, and you align everything in just the right way so the laser goes where you want it to go. And in our case, goes into the place between the two mirrors where the light gets very intense. And on the right, I'm showing a photo of something I haven't actually talked about, using a pulsed laser. That's me playing with a very intense pulsed laser, which we use for detection in the experiment. And I'm burning a piece of paper with it, not because I'm a pyromaniac or anything, but because we actually need to see the beam. And like I said, this experiment is really in a build phase. So we don't have a working experiment right now where I can just plug in molecules and show you how they react. But the hope is that one day we will. And one day we'll have an experiment based on all of the technology that I've talked about in this talk that looks schematically something like this. Molecules will be attracted into a laser, they'll collide with each other, and we can watch in real time as quantum chemistry happens. Thanks for listening.
Wow, Ashwin. So many cool things going on here, not to mention that the incredibly low temperature you establish in this chamber. I see some applause. Billy, thank you. I don't see a raised hand, so perhaps the Wondernauts will allow me to ask a question or two. And I ask for your forgiveness because I was a high school physics teacher for a very long time, and that image of a light beam taken with the electron microscope blew me away. Do you mind showing us that image again, Ashwin?
Yeah, absolutely. No, it's it really is something incredible. It's like, yeah, this is the image.
And I take it, since you described this as a light wave, we're seeing dark and light bands that represent what, in old-fashioned terminology, might represent the crests and the troughs of this wave train?
Yeah, so there's a couple of things to say here. So crests and troughs, that is even the language that I used. But maybe I'll be a little bit more specific right now. When I say that the light is bouncing back and forth between two mirrors, what it forms is a standing wave rather than a wave that's traveling. And so what you're seeing are technically the bright spots are the antinodes of the standing wave, and the dark spots are the nodes. You could picture like waves on a string that's fixed at both ends, and you get some points where the string oscillates a lot and somewhere it stays still. And the same thing is happening with our light wave here.
Ashwin, thank you. Yeah, the jump rope wave, the traditional jump rope wave, even when spun in a circle, is a form of standing wave. Yeah, great, thank you. I see that Gary, a great Wondernaut, has a question there. Gary, please make yourself visible, and there you go. Ask away.
Is there a mechanism for removing the heat generated by the laser to maintain near absolute zero, or how do you control the temperature?
That's an excellent question. So the question, I think, comes from the idea that lasers cause a lot of heating or are very hot in some sense. And I want to tackle that in two ways. The first thing I want to say is that lasers don't have a temperature. So lasers are not hot things. They don't actually have a temperature. And the way that you can think about this is maybe if you think about stars, and I'm going to use a little bit of a leap here, but you might know that stars are very kind of like cool stars glow red and warm stars glow blue. And our sun is somewhere in the middle and it glows sort of yellowish white. But our sun, even though it looks yellow or white, it's giving off like all of the different colors of light at the same time. And so its temperature, when something is very hot and is glowing, it gives off lots and lots of different colors of light. A laser gives off exactly one color of light. And so it's fundamentally different to something which is hot and radiating. Now, what a laser can do, this is the second part of this question, is it can hit something which absorbs the laser light. And that means it absorbs energy and it gets hot. And so what we actually do here is the molecules that we're using are not absorbing the laser light. So they actually don't get hot from the laser at all. So we don't need to worry about that thing. The heating rate, you can actually calculate it, and that's one of the things that we've done when we were designing the experiment. The heating rate is each molecule heats up by about 0.01 millikelvin per second. It's really small. So the molecules just really don't absorb much of the laser light, and so they don't heat up. So we don't need to worry about that. It's a really good question.
Yeah, thank you.
Thank you, Gary. Ashwin, let me ask again, since you finally got that photo up of the standing light wave there. You mentioned in optical tweezers, a laser beam's ability to hold a molecule, perhaps an individual atom even. Mm-hmm. Is the fact that you're showing us a standing wave there relevant? Do the optical tweezers rely on this principle of standing wave formation?
So the optical tweezers work for either standing waves or traveling waves. It doesn't actually need it. The optical tweezers work basically, so the light is an oscillating electromagnetic wave. That means there's an electric field which is oscillating up and down, and that pulls on the electrons in molecules or atoms or whatever you want, and they move with it. And now the electron that's moved around protons or nuclei or whatever, that combination of things wants to go to the region, like it's very happy in that state where it's been polarized by the field. And so it just means everything is attracted to light. That's all that's happening here. So everything gets attracted to wherever there is very intense light. So in this picture, where I just have light going one way, there's no kind of nodes and antinodes, things get attracted to the middle, to the focus of the light. In this picture here, where there are nodes and antinodes, the molecules will be attracted to wherever it's bright, and they won't be attracted to wherever it's dark. So there is a difference slightly between how the optical tweezers work, but the only thing you have to remember is just, everything gets attracted to where the light is. So that's it.
Wow, Ashwin, thank you. It's hard to reconcile that with, let's say, the formation of a comet's tail, not the formation, but the pushing of the comet's tail away from the sun by the pressure of sunlight. In that case, we see light not holding something, but pushing it away. But I take it that's not laser light, and it's certainly not this configuration of laser light.
I will mention that is actually a concern. And so there are different regions. If you have just a laser that's going in one direction, there are different regions of the beam where that pressure force beats the attraction force. But in our case, where we have a standing wave, you can think of as two lasers that are kind of hitting on each other. So that sort of balances out, and right near the focus of our laser beam, we don't have to worry about that force at all. So no, that is a very good point.
Oh man, Ashwin, thank you. Billie and Ashwin, we'll return in just a moment to give you genuine thanks from everyone here. But I want to thank every Wondernaut who's shown up tonight. And I know that you're looking forward to future Ask a Science Envoy events with the Berkeley Public Library. I hope those will be coming to you probably starting April of 2024. Exciting. All right. Again, thank you, Wondernauts. Thank you, especially you Wondernauts who are supporters of Wonderfest. Perhaps your patrons. That's very kind. Wonderfest survives on your generosity. But most of all, please join me in thanking, perhaps with American Sign Language silent applause, Join me in thanking Billie Goolsby and Ashwin Singh. Good night, all. See you soon, I hope, perhaps in person. Good night, all.